Hi, everyone. Welcome to the session. Thank you for joining me here today. A quick introduction about me. My name is Jayeeta Putatunda. I am a data scientist working with MediaMath, and I am based out of New York City. If you want, you can connect with me via LinkedIn, Twitter, as well as my website, and I look forward to connecting with you all here. So today I'm going to talk about um, in NLP and just walk through a little bit of example of how we can use some of the pre-trained models that's available in the industry and use that for a little bit of information extraction techniques. Before that, a quick overview on what we're going to cover today. So just in a high level, look what NLP is, why do we need transfer learning, and what are some of the use cases we want to use transfer learning for, and then look into the differences between BERT and DistilBERT, and like look into a quick code base on how we can use the transformers DistilBERT model to kind of create a fine-tuned model in our context. So this is an image that I start with all the time, and this gives a very overview of why NLP sometimes can get tricky. So when you see this image of a fan, it says, I'm a huge metal fan. For a human being, it's very easy to make the connections and references very quickly. But then for a computer language, it's very difficult to distinguish between that. Are you a huge metal music fan, or are you an electrical appliances who is like you're a metal electric fan? So this ambiguity, this synonymity, co-reference, and some of the syntactic rules that's present in English language kind of makes NLP a little tricky, and that's why we see that there's so much development that's going on in the field right now, in terms of research, in terms of elevating the accuracy scores that we are getting for some of these tasks at hand, and hence we see that not only artificial intelligence and ML, but linguistics plays a very crucial role, and that's why I feel that this combination together is only when we understand the English language in a very deep level, we'll be able to answer some of the tasks that we have at hand. In the past, like last maybe 3 to 4 years, we have seen like a huge transformation in the research space, and large scale language models have been significantly developed and improved upon. And if you see in the image here, the latest model that was released end of February 2021 was the switch transformer from Google, which has like almost 1.6 trillion parameters, and that's like a huge number of parameters that we are dealing with, and it only gets larger and larger, being trained on bigger data sets. So why do we need transfer learning in the NLP model space, right? If you think about it from this scenario, say creating high performing natural language models is time consuming first, and secondly, it's super expensive. So it took, like, just to give you a little bit of context, it took the Google Brain team like almost 3.5 days on 8 Tesla P10 P100 GPUs to train all 340 million parameters for their first level of large scale model that they released. And this is inception since 2018, I guess, like 2018, natural language models have only increased in complexity. Like we just saw in the chart, right? The number of parameters being used has like increased exponentially. So what if like a company or like say you're a researcher working to develop some of the models doesn't have the resources that you need to train such large scale models, right? So these advances in transfer learning is like the concept where companies like this can more easily achieve state of the art performances by simply adapting to the pre-trained models for their own natural language tasks at hand. And similarly, this image just portrays the same thing, right? Like if you have different learning says that, or you will create 3 different learning systems to kind of address that task. But then what transfer learning is saying, that you have a source task that is like similar kind of uh, context that the target task has, and then once you train the source tasks and you create a knowledge base, you can basically leverage that knowledge base to kind of create a learning system that your target task can help with. And we will see in details what that looks like in some examples in the code. But when do you use transfer learning, and what are the some of the situations where it's the path to go? First, where you have scarcity of labeled data, because we all know like creating labeled data set is like expensive. There's like time and expert resources that needs to be part of the system, like subject matter experts in the training process, and only then you will be able to make sure that your data is not biased or it's tagged correctly, etc. Secondly, when you already have a pre-trained model that's trained with a huge data set, and you have that source data that we saw in the previous slide, and the second is that the third is we have to make sure that the task one, and that is the source task, and the task two, which is the final task, have like similar input properties. And by that I mean that you should be able to transfer the knowledge that you have learned from the source task to the target task. And say an example, you have image that's your source task. You cannot like possibly use that source task for very unstructured based legal document parsing as your task too, right? Because the input properties are not same, they are not coming from the same background context. So here are some of the examples, like very classic examples. In the right hand side, you have task one, where you have access to a massive amount of data set. Like if you think about the second example, like very classic example from the computer vision field, like you have ImageNet with millions of tagged images, right? And it has trees, houses, etc. But then when you want to do a task two, where you have less data set with, say example, for the image recognition, you want to identify if it's an urban image or a rural image. So it's not that you have like humongous amount of data tagged with urban, rural. Instead of that, you can basically use the ImageNet data set that you have learned to identify which objects belong to which category, and then use that in your transfer learning process to kind of fine tune and build up on your image recognition process. So today we're going to talk a little bit on a high level about what BERT stands for, what DistilBERT is, and how basically we can achieve our information extraction task using DistilBERT. So BERT was like first of its kind. It was the first deeply bidirectional model that was pre-trained on plain text. If you see some of the trained model, it is used like 2,500 million words from Wikipedia, book corpuses, and etc. The concept behind BERT is that it will learn the information from both the left and right side of a particular word in a complete sentence during training. What it does, that it brings out the context, and context parameter is very crucial in BERT, because this is what this is a step that solved some of the challenges that we had with previous versions of tokenization and learning, like example in Word2Vec, where it was not necessarily using the both trailing as well as the leading words at the same time and understanding the context in a similar manner. So context meaning is that it'll be learning from both their adjacent words. And here, if you see that the basic idea of it is that learning from both sides is going to create a word piece embedding and represent that particular word token into the entire vector space. A quick example here. So you see here we have two sentences where it says that, okay, we went to the river bank, and then I want to go to the bank to make a deposit. Now both of the sentences have the word bank, but then it has different context, and that is getting determined by the pre and the post words like river. So when you're talking about bank in terms of river, we know it's not a financial institution, it's like riverbed. And then in the second one, you see that it's highlighted as a context is that to make a deposit. So that's where we're getting segmented, saying that bank is a financial institution here. A very high level understanding of how BERT layer works. So there are three segments to it. Token, think about token as like a particular word or the tokenized version of the entire sentence. So here, if my sentence is say, my dog is cute and he likes to play, etc. Then the token embeddings will be each of those words segmented, right? Like my dog is, etc. So that is one level of processing that BERT does. Second is position. So here the idea is that we are able to capture the word-to-word relations, that which word belongs next to each other, right? So when you see the position segments in the third segment, you see E0, E1, E2, because it's marked that where is it placed in a particular sentence. And then we also have the segment, which is the sentence to sentence relation. So if you have, like, say, two sentences together, here, my dog is cute, full stop, he likes playing, full stop. So it's two sentences. So the idea is to basically understand if the next sentence belongs to each other. We'll see example in the next slide. But here we are basically tokenizing and inserting these classifiers and separators in order to understand where we mark the differentiation between multiple sentences, how are we tokenizing, and what is the relation between each of those words in the position embeddings. So BERT is basically pre-trained on two NLP tasks. One is the mask language modeling, and the other is the next sentence prediction. So mask language modeling is the first example that I am showing here, is that it tests the strength of bidirectionality. The idea is, like, say you're training on 1.6 trillion parameters, there is bound to be, a similar sentence or a similar combination computer will find. The idea is, if we are masking some of the words in the sentences, the computer learning from the context, or the algorithm learning from the context, will be able to fetch those words, even if for that particular sentence the word is masked. So in this example, it says the man went to the word is masked, and then he bought a dash of milk, which is a masked word. And then the labels that the algorithm will be able to identify is store as well as gallon, which kind of makes sense because we are learning from both the left and the right side of the contextuality and understanding the context of it as a whole. And then there's like the model relations between sentences, saying that, okay, the man went to the store and he bought a gallon of milk. Is this the next sentence? Does that make sense? Yes, it's a label is yes, it's a next sentence. Otherwise, it's not a next sentence. Now, that all makes sense, but why are we talking about DistilBERT? The main reason is the biggest challenge in this space is, like, how do you put these huge models into production? Because if you're not able, like, use it in production in a low latency constraint, how are you going to utilize it for serving your business purposes? So do we need costly GPU servers to serve at scale? So for many of academic researchers and small companies, these are like deal breaking issues. And here the potential solutions that comes up is the concept called knowledge distillation. In a simple term, it's nothing but compressing the entire technique in which a small model basically is trained to reproduce the behavior of a large model. In this example, the large model is our BERT base, and the new model that we will find from the compression is the DistilBERT. So how is it done? The general theory is that it's a teacher-student training network, and a student network is trained to kind of mimic the entire full output distribution of the teacher network. And our teacher network, like I mentioned in our case, is the BERT base that was released earlier. This is a very clear example. Like, if you can see the example sentence, it says that I think this is the beginning of a beautiful dash. So that dash is the masked word. Now, if you see some of the ranked results with probabilities, it's like the word is like day, life, future, story, world, time, etc. And all of those make sense because, in a classification model, the predicted output distribution with the correct class will have high probability, and leaving some of the other classes probabilities near to zero. But then some of these almost zero probabilities are larger than the others, right? And this reflects the generalization concept that we are generalizing. We're not sure if this is the right answer, but this makes sense. And that is a generalization part. A quick example, like a desk chair can be mistaken as an armchair, right? But then it shouldn't be mistaken with, like, say, a food item like a mushroom, because and this is where that generalization takes place, and this uncertainty is sometimes referred to as dark knowledge, is what DistilBERT is trying to get and learning from the distribution from the BERT's output. And what is the result? The result is, like, we came across like a smaller language model, the DistilBERT. It's built from the supervision of BERT. It's 40% smaller, but it retains like almost 95% of BERT's performance. I quickly wanted to show, I know we kind of lost a little bit of time, but quickly wanted to show how you can use the transformers segment. So you can just call the pip install transformers model 2.8.0 or whichever is the current model. Here is what we are doing is basically calling a pre-trained model. If you see this line, that we are calling a pre-trained model, DistilBERT base uncased. And this context that we are giving is the transfer learning's fine-tuned method that we were talking about. That this is the context that we are giving for our case. And you can imagine, like in an NLP use case, it's nowhere possible that you will give only this much of context data and be sure that you will get a positive or correct answer. And that is being possible because we are utilizing the pre-trained model from DistilBERT's base use case and using that in our model scenario. So here, when I give the context, say just, okay, case numbers in the United States have fallen, etc., how many number of people have been infected by COVID-19, etc. So when in this question, when you're asking that what was Joe Biden president's announcement, when you see the answer tokens that the model fetches is that, okay, his administration is donating 500 million doses of etc. So then the complete answer token would be that, okay, his administration is donating 500 million doses of Pfizer vaccine, right? And then how many deaths have been reported? The context here that the deaths have been reported as this many numbers, and that gets fetched, or the information is extracted from the context that we gave by using the pre-trained data that we have already been using it on top of it, right? So this is like the last step of where you're fine-tuning the BERT-based models, the pre-trained models, and then making sure that we are utilizing that in a correct context from our end. Just to leave you with some positive notes, like sometimes, we think that we're going to train, AI models all the time using some of the resources that we have at hand. But if you look at like some of the implications or consequences of building such huge models, it takes the MIT report said that training a single AI model can emit as much as carbon as 5 cars in their lifetime. And we have to make sure that we are taking or using the resources that we already have without trying to build everything from scratch, building it from our end just because we can do it. So just a quick insider tips, make sure that on all your NLP models, the data cleaning is the best thing that you can do to make sure that your model performs well. There's no shortcut in that. And most of the time, the advanced NNs maybe or neural networks may not be your best solutions just to make sure what your data actually is looking for, what your business case is the best path to go. Thank you to the team. I know we had a little bit of glitch at the forward, but if you have any questions, please let me know and I will try to answer as much as possible. And please feel free to reach out to me via LinkedIn as well if you have any further questions. I think I almost went over time and I'm going to stop the broadcast here and look forward to connecting with all of you. And thank you for joining the session. Thank you.